Okay, so I tried to record this hour-long video driving this messy formula, and of course the audio didn't record. So I'm going to just explain really quick what we did. So this is relativistic velocity addition. Let's pretend we have this ship moving at a speed 0.8 c that shoots a laser c. Classical mechanics says, okay, well, the speed of that laser by an observer O would be 1.8 c. That's not what we observed. It's not what Einstein says. So this is a failure of classical mechanics, and we need a new way to add velocity vectors. Okay, and I'll go ahead and spoil it for you if this is all you need to know. The velocity is equal to v prime plus u over 1 plus v prime u over c squared. But if you want to see it worked out, I did work it out. It just took a long time. So imagine we have this system where a particle moves at the speed v, that's the blue, from P, hits F shoots out light that travels a speed c to the detector, and that's one click. The whole thing's moving at speed u. Kind of like length contraction, we can derive the exact same equations to describe its position and distance. We find its time, L naught v prime plus L naught c, from O prime's point of view. And then we can derive our time intervals just like we did before, with length contraction. We introduce the notation gamma, which is 1 over the square root of 1 minus u squared over c squared. And we changed our length contraction formula over here, and our time dilation and length contraction here to use gamma. It makes the math easier. Notice if we multiply delta t naught by lambda, right? Our delta t naught was equal to up here. So we multiply that whole thing by lambda, and you have delta t. That's this. Well, we can set our two delta t's equal to each other and replace L naught with gamma. Well, we replace L naught with gamma L, which gives us gamma squared. The L's drop. Multiply both sides of the equation by the denominators, so v prime, c, v minus u, c plus u. Now the nasty part. Everything that doesn't cancel, you have to multiply through. So we do that. Things cancel. I foiled this stuff first, and then distributed the lambda squareds. I moved everything with v to the left and everything without a v to the right. I factored out a v, and then on the right-hand side, I factored out a negative gamma squared from everything except this part. This guy just went there. I divided it over to get v by itself. And then we did a little bit of a tricky little thing. We multiplied by 1 over gamma squared divided by 1 over gamma squared, because that's just 1. And what that does is this 1 over gamma squared cancels with this, but not with this guy. And it cancels with this, but not this guy. But remember, 1 over gamma squared is just 1 minus u squared over c squared. Right? Because you flip it and then square it, your radical moves to the top, and then squaring it gets rid of it. So I plug that in, and then we multiply by c over c. Okay? And what that does is we just multiply everything throughout. We obviously distribute this, and we distribute this. And then you get here, and you multiply by negative 1 over c squared divided by negative 1 over c squared. So that gets rid of our negatives, and that knocks out a whole bunch of our c's, with the exception of a few. Going over, we can get common denominators, and you get to this guy. Notice for the v primes, you can factor out a c plus u, and for the u's, you can factor out a c plus u. And then from here, we can also factor out a c plus u. The c plus u's all drop, and you get v is equal to v prime plus u divided by 1 plus v prime u over c squared. And that's it. It took about an hour to actually derive that and explain it all, and I don't have the time to do that, and I don't think I want to wait that long. If you guys really want it, I can just do it, but I don't think it's entirely necessary. If you're really curious, hopefully that was enough to get you through the algebra, and we can start doing examples.